In 2019, for the very first time, an image of a black hole was published. This image was of a supermassive black hole at the centre of the galaxy M87. To date, these supermassive black holes are the largest black holes found in the universe and can have masses several billion times the mass of the Sun. When a massive enough star consumes all its nuclear fuel, it results in a giant explosion called a supernova. The remaining material is now under the huge influence of gravity and collapses into an infinitely small region, a region where the gravitational pull is so strong that even light cannot escape. This region, where space-time bends to infinity, is what we call a black hole. It is thought that all galaxies, regardless of their size, contain a supermassive black hole at their centre. But how are these gigantic black holes formed, and how do they affect the dynamics of their host galaxies? Today, to answer these questions, we have Dr. Becky, an astrophysicist at the University of Oxford, who also turns out to have a very popular YouTube channel.
Yeah, so finding out there was a supermassive black hole at the center of our own galaxy is like one of my favorite stories in physics in general. So we had a telescope in Hawaii that actually studied the movements of the stars at the very, very center of our galaxy for decades, and they saw the positions of those stars change obviously as they orbited around the thing at the very center. Now, if you know the orbits very well like that, and we've actually seen a star do a full orbit around the center now in the past sort of 15 years, which is very exciting, then if you can plot out their orbit, then you know how fast they're moving around the orbit and what all of the properties of that orbit is. And so with that, because we know gravity so well, with Einstein's general relativity, we can then work out how big the thing is they're orbiting around in the very center of the galaxy. Mm-hmm. And so that's very exciting, because when you do that, you find that it is huge. But you also don't see anything in the center of the galaxy either. So that's very interesting. And it sort of says, okay, well, there's clearly something dark that's there that's incredibly massive. So what is it? And when people first figured that out, there was a lot of debate about whether there was perhaps a swarm of black holes in the center of the galaxy, because we didn't realize that black holes could get that massive necessarily. We thought they were more sort of like, 5 to 10 times the mass of the sun, not millions of times heavier than the sun. But a swarm of black holes would completely break apart. Like, if you can imagine a swarm of black holes, it would be so chaotic. There were things flying past each other all the time. They would be sort of like slingshotted out all the time. And you obviously don't see that. It's a very stable thing at the very center of the galaxy that, even the sun is technically orbiting around as well. And so that was how we figured out that it had to be a supermassive black hole.
And is that how we also know that other supermassive black holes in other galaxies exist?
Yeah, so I think that definitely gave us a clue to what was at the center of other galaxies. If there's one at the center of our galaxy, then maybe there's one at the center of others. When we observed other galaxies, we also saw these things called quasars. So this might be a word that people have heard thrown around a little bit, but these are incredibly, incredibly bright galaxies. And in particular, light is coming from the very center. Now, you might think, well, that's weird. Black holes, the whole point of black holes, right, is that they don't give out light. But actually, the material that spirals around a black hole is essentially like superheated because it's going so fast, being sort of like sucked into sort of like a plug hole of the black hole, if you will. And so that material is what glows so brightly. And so there was, for a long time, people were puzzling, well, some galaxies we see X-rays from the very center, and some galaxies we see radio waves, and some galaxies have these strange jets that come from the center as well. And eventually, especially after figuring out that the Milky Way had a supermassive black hole in the center, and also from observing much smaller black holes in our own galaxy that also glowed in X-rays due to this process that we call accretion, this sort of like pulling in of material into this disk that spirals around the black holes and is superheated and glows. People figured out, well, it's that process happening around other black holes at the centers of other galaxies that we're observing, but on a much larger scale than we'd ever seen before.
As you already mentioned, the size of the supermassive black hole at the center of our own galaxy, how massive can these supermassive black holes get?
Yeah, so I mean, our galaxy's black hole is only 4 million times the mass of the sun. I say only, right? Because it is tiny on astronomical scales, but like to us, it's not. In terms of how massive they can get, that's a really interesting question. So the most massive supermassive black hole we know of is 66 billion times heavier than the sun. So 4 million for our galaxy and 66 billion. So these things can get a lot bigger. People often then model what they think will actually happen around a black hole in terms of how this material gets, eaten by the black hole, for want of a better word, right? And the way that this happens is if the material is moving too fast, then it'll never end up going into the black hole, at least if it's not crossed that event horizon, that point of no return where you have to be traveling fast in the speed of light. And so if it's traveling that fast, then the black hole is never going to get a chance to eat it and grow with it. So what people have suggested actually happens is that in that accretion disk, essentially particles collide and they exchange angular momentum, right? They give energy to another particle that's further out in the disk so that they can lose energy and slowly fall in. The thing is, obviously, they only fall in if they cross the event horizon. Now, as a black hole gets bigger and bigger and bigger, actually the radius at which you can get something orbiting around the black hole like that, like spiraling around, gets pushed further and further out until at some point we think it actually crosses the event horizon. And so even if you've got particles losing energy to get closer and closer in, if at that point, they can no longer form a stable orbit and they've got so much energy, it'll just fly off and it'll never actually get eaten by the black hole, which is a really interesting idea. So when people think about that, you hit a limit that's somewhere, depending on what assumptions you make and what all the stuff you put in your models are, between like 50 and 70 billion times the mass of the sun. Now, of course, that only means that they can grow that much by accreting material. You could get two black holes that would merge, right? And that would double their size. That'd be another way to grow. But it's an interesting idea, that especially since that heaviest supermassive black hole we know is 66 billion times the mass of the sun. Like, it's getting at that limit. Like, we could be living in the era where we're at the point where black holes are reaching the heaviest they're going to get, which to me is like incredibly exciting. I think that's really cool.
So we've said how massive black holes can get. Going back to the opposite end, how are they formed initially?
The main way that we think black holes are formed is through supernova of stars, right? So this is stars that are, say, 20 times heavier than the sun. And what happens when they run out of fuel in their core, so this is the area where it's actually hot enough for nuclear fusion to actually happen, right? So around that's just sort of hydrogen that's keeping the star sort of massive, but it's not actually being used as fuel. And so what happens when it runs out of fuel and stops burning hydrogen in nuclear fusion in the center is that all of a sudden all those outer layers are then very heavy and there's nothing to restrict them collapsing inwards. What happens is they then collapse inwards, they rebound off that center and get thrown out into space. That's the supernova. But then that very central core just collapses down into a black hole. So that's how we think black holes of, say, 3 to 5-ish times the mass of the sun are formed through supernova. But that's not supermassive black hole variety at all. It's nowhere near, right? Those are the kind of thing what we call stellar mass black holes. And so the jury is still out as to how you either go from, in the very early universe, you maybe form your very first star and very first galaxy. One of those happens to go supernova and form a black hole that's pretty small on black hole standards. And then does it grow and grow and grow until it reaches millions to billions of times the mass of the sun, like now in today's universe? Is that what happens? And is it because, as it starts to grow, that black hole in that galaxy, it becomes the heaviest thing, so it sinks to the center and everything starts to orbit around it, and that's what gives us sort of these nice disk galaxy shapes like our own Milky Way? Or in the early universe, does somehow a black hole form that might be tens of thousand times the mass of the sun, something where you've just taken a cloud of hydrogen gas and it's just clumped together, somehow stopped from forming stars, and instead has collapsed down and formed a black hole? And so that's sort of the debate that's raging at the minute in the astrophysics community, is how these supermassive black holes start life. Do they start from the piddliest and grow up, or did they get a little bit of a head start, and did they form very large in the early universe from the beginning? Such an interesting avenue of research. Very theoretical, but actually there's some observations coming out now that suggest that actually we could be observing that happening as well, like a cloud of gas that's being illuminated with lots of radiation, and so therefore heated and stopped collapsing down into stars. And so we think that thing might be a candidate for something that could collapse straight down into a black hole.
As you've already mentioned, the observational evidence for the existence of black holes, such as from the motion of the surrounding stars, it wasn't up until last year that we had a direct image of a black hole. and I watched your live reaction in seeing the first image of a black hole for the very first time, and you were so excited. So why was this first image of a black hole such a huge breakthrough?
I mean, I don't know about anybody else, but to me, getting an image of a black hole, something that doesn't interact with light, so we can't ever be able to actually see because there's nothing almost to see. That was just sort of out of the remit of what was possible to me. And then the fact that in 2019, they managed to actually take an image of this material that is spiraling around the black hole, very, very close to that event horizon, right? So that they actually saw the area where you were getting light and then all of a sudden not getting light from, right? They called it the shadow of the black hole, right? That to me was just incredible, that something that I never thought I'd really be able to ever see because it wouldn't be physically possible to see, that you could actually see the outline at least, or the shadow, or this sort of like hint that that was actually there. That blew my mind. And I remember thinking that it wouldn't look that great, right? It's so far away, the black hole they took the image of. It's in the center of another galaxy that's billions of light years away. Yes, it's massive. It's sort of 1,000 times more massive than our own Milky Way. So 1,000 times bigger as well. So it makes it quite easy, she says, to spot in comparison. But like, I imagined it to sort of be like a couple of pixels, like there'd be like 3 pixels in the middle that would be sort of slightly black, and then everything else would be sort of like the emission that they detected. But the detail in it was incredible. That's why my live reaction, I was like, I was actually took aback, because it's not what I expected to see at all. It was so much better. And then it was so funny, like listening to the public's reaction of going, is that it? It's just an orange donut. I was like, yeah, but it's like the greatest orange donut ever, So it was really funny to see sort of the differing reactions, and then explaining to people that like the black in the center is where there's so much stuff that you're not getting any more light, whereas the black around the outside is like empty space. It's it's the differing sort of aspects of the image that make it so spectacular.
And what are the challenges of taking an image of a black hole?
Yeah, I mean, obviously, first of all, it's going to sound weird when I say this, but black holes are really small. They might be massive, but they're really small because they're so dense and so compact. So the problem is always going to be resolution. What's the smallest thing you can see with your telescope? And so with a normal telescope, like picture a dome that opens with this nice big dish that comes out, even with something like the new generation of telescopes that they're building that are like 30 meters across, huge, extremely large telescopes that are being dubbed, that they wouldn't have a chance of seeing anything that small in the sky. And so what the Event Horizon Telescope team did, which is the telescope that took this image, is actually made a telescope that was essentially the size of the Earth. They combined many telescopes across like all continents, basically, of the Earth. And so if you can up the size of your telescope, you can therefore reduce the size of the thing that you can see. And so that's how they were able to actually take this image of something that is incredibly small, but also incredibly, incredibly massive.
And will we expect to see an image of the supermassive black hole at the centre of our own galaxy?
Yes. So the Event Horizon team, they had 2 things that they were like, this is the 2 things we're going to do. Messier 87s, which is the one they released in 2019 already, because it was the nearest biggest black hole. And actually, by sort of sheer coincidence, because it's so much bigger than the Milky Way, but it's also a lot further away than the Milky Way's black hole, because obviously that's our own galaxy, it makes it about the same size on the sky, sort of from our perspective. And so they knew that like our Milky Way's black hole, and that was something they'd be able to target. Now, the problem is with the Milky Way's black hole, you're looking through, obviously, all the stars of the Milky Way towards the very center. And the closer you get towards the center of the Milky Way, the more and more stars there are, the more and more gas there is, the more and more dust there is. And dust blocks a lot of light, but it can also absorb light and then re-radiate it. And so it's very difficult to like see past all that. And then also know that like what you've recorded as maybe being from the black hole is actually from the black hole and not something in the foreground. Whereas with Messier 87, they could point sort of up and out of the galaxy and didn't really have to worry about that at all. So it was very interesting that actually they released the M87 one first, because you would think the closest one to home would be the one that they'd be able to do first with our own Milky Way black hole. But because it's a similar sort of size, and because there's just so much to look through. It's, you know, almost like not being able to see the woods for the trees, essentially. Like, it was actually much easier to get a clear image from the Messier 87 black hole first. So the last I heard, which was back in November, when someone from the collaboration came and gave a talk to us, was that they're working on it, but it's proving very difficult. And there's lots of things that they have to account for. They have to remove what they call foreground sources, all the stuff that's in the way, and make sure that they're not removing anything that's background light that they actually want, you know. So it's very, very difficult. I think it's taken them a long time, a lot longer than they thought it would. And I'm sure the pandemic has not helped situations either. So we might be waiting a little while longer yet for it.
So you've already touched on this a little, but maybe in more detail. How do you go about studying a black hole?
Yeah, so that's the thing. Everyone always asks, like, how can you study or observe? Because I say I'm an observational astronomer. I use telescopes to observe these things. And everyone's like, you just said you won't see them. But the thing is, you really do learn a lot from studying the material around it, whether that is the gas that's spiraling in, or whether that is the stars that's orbiting it from the center of our Milky Way. You can learn the mass of the black hole, you can learn how it's spinning or rotating, you can learn the rate at which it's taking in material, all from that disk of material that's spiraling around it. So you can get a lot from that. And so one of the things that, you know, I'm trying to do specifically is work out what effect the black hole has on its galaxy, right? Because something that massive in the center that's, you know, drawing a lot of material in can obviously have a huge effect. And also, one thing that also does happen, you've got this material that's superheated and it's glowing, very, very energetic. You build up a lot of pressure around a black hole. And so we talked about that limit before that they can reach, but there's also a limit at which they can actually take in material, just because the pressure around it grows so much. The same way that, you know, you take a plug hole out of a bath, the water doesn't just all drain completely because there's this pressure stopping it from all going down at once. And so what we're trying to get at is, when that pressure is released, actually, instead of all the material being sort of funneled to the black hole, some of it is actually turned around and shoved back out into the galaxy. Like, nope, you know, we've reached capacity here, you know, like you guys are out. And so if it's throwing material back out into the galaxy at huge energies, like, what is that doing to the galaxy? And the theoretical community has been saying for ages that what it does is it heats up all of the gas in the rest of the galaxy that would be used for star formation. You need very cold gas for star formation because it needs to be not moving very quickly so that gravity can have its way with it and pull it down into a star. And so by heating it, you then stop the galaxy from forming more stars in the future. And so then that stops the galaxy from growing any bigger. And so theoretical astronomers have been saying for ages that this output of energy from the surrounding areas of a black hole has got to stop galaxies from forming stars and then stop them growing too big. And if they don't include that in like simulations of the universe, you get too many big galaxies, just far too many. And so what I'm trying to prove is that that is actually happening. Like, I'm trying to observe it with telescopes. I'm trying to go, okay, what's the properties of the black hole? What is it doing? What rate is it taking material in? Is it past that rate? Okay. Can we find evidence of it outflowing material as well? And then what's the galaxy doing? Like, what are the stars doing in the galaxy? Like, what rate of star formation is happening there? And is that correlated with the fact that the black hole is growing or not? And it's trying to sort of find that smoking gun of like, okay, energy from this black hole is affecting this galaxy in real life. And it's happening across a huge population of galaxies, not just like one either, right? You know, like, one's no good, 2 doesn't make a trend, 3 you get in there, but like ideally you'd need this huge sample to get statistics. And so it's a really difficult thing to find because there's so many variables and so many other things that can also stop a galaxy from forming stars. It's hard to piece it out. But there are ways that you can study black holes despite all the limitations. And there's very clever ways that people do it too.
That's great to hear a bit more about your research as well. So as you've already mentioned, the ways in which we can study black holes, what remains to be known about black holes?
A lot. If we knew everything already, right, we'd be out of a job. But there's so much we don't know. You know, like I said before, we don't know how they formed. Really, like, there's jury's still out on that. We don't know, you know, what they look like beyond an event horizon. We don't know even if black holes could actually be the reason that there's so much dark matter in the universe. What if black holes are the explanation for dark matter? That's an interesting idea as well. We don't know how those really, like, the very intricate details of how that material gets thrown back out again. We know it's something to do with magnetic fields. Magnetic fields is something in astronomy that's like it's like a joke. It's like no one's ever thought about magnetic fields, right? That we always sort of like think, oh, it's too complicated. People are working on that to try and understand that better. And so I think, to be honest, I think I'd be safe in saying there's more that we don't know than we do know. And there's a lot still to find out.
Black holes are one of the most mysterious objects in the universe. There are still lots of things we don't know about black holes at the centres of galaxies. Soon, we may see an image of a black hole at the centre of our own galaxy, the Milky Way. The more information we get from these supermassive black holes, the more we will know about how galaxies are formed, why the universe looks the way it does today, and how it will look in the future. Hi, the Arts of Physics YouTube channel is now publishing videos regularly. Don't forget to subscribe and activate notifications so that you don't miss any future videos. Thank you for watching.